Yeah. Okay, we might move on to our third speaker for today. Thank you, Stan. Yes, our third speaker.
Yeah.
Yeah, our third speaker is a colleague from Queensland, Roy Axelsen. He's been dabbling with a new portable photometry rig, which is proving to be very capable of very high quality photometry in a relatively economical package. So I'm very keen to hear Roy's findings, because I might be going down this path myself with another system. So Roy, if you would like to take over.
Thanks, Mark. I'll just try to share my screen here and expand that. Is that visible for everyone?
Yes, we can see that, Roy.
I'll try reading view to see if I can make it better. There, is that good?
That's fine, Roy.
Yeah, I'm not seeing anything.
I'm sorry?
I'm not seeing anything on my screen. It's just saying David O'Driscoll has started screen sharing.
I stopped screen sharing a while ago, Mark. I think your bandwidth is killing you.
That's my internet.
Okay, I'm certainly seeing Roy's screen.
I am now.
I've got the title slide on the screen at the moment.
Yeah, seeing it now, Roy. Thank you.
Okay, good. Here we go. So the acquisition of this equipment occurred in two stages. I purchased the ZWO camera about 3 years ago. The Star Adventurer mount is a more recent purchase, and it's the latter that I want to concentrate on, but there'll be some introduction before then. Just excuse me a moment. When I first started out with photometry on digital images, I started with a DSLR camera and an 80mm f7.5 refractor. Once I was properly set up, I used auto-guiding as well. This is a fairly inexpensive rig, commercial grade mount, so the whole lot didn't cost very much. I rather like this because, of course, with DSLR photometry, you can do 2 and 3 color photometry, and the results could be quite stable, even across a long period of time throughout the night. With delta scuti stars, it's fairly easy to find comparison stars which are approximately the same color, which without any extinction correction can still give rise to quite stable light curves. So I enjoyed doing that. As with all DSLR photometry, images need to be defocused, and this is one of the focuses of this talk, so that the Bayer matrix allows each channel to be spread across a number of pixels. And of course, that means that the full width half maximum of stars is quite large. For example, in this particular image, it's about 20 pixels. And you can see the same thing if you do a line profile through the defocused star. But following DSLR photometry, I purchased this camera, which is a ZWO ASI1600MM Pro. The MM means that it's a monochrome camera with a monochrome sensor, and it's a CMOS camera. The specifications are shown here from the manufacturer. The sensor is a Panasonic sensor. It has 17 by 13 millimeters in size, which is quite reasonable, 16 megapixel. It only has 12 bits. It's just 12-bit ADC, which is the big disadvantage of this camera. The pixel size is relatively small, 3.8 micrometers, but not as small as these cameras can get. I'll refer to one towards the end of the talk that had a 2.8 micron size. The full well is 20,000 electrons, but that's only at a gain of 5 electrons per ADU. The native full well is only 4,000 electrons, which is, of course, what you get with 12 bits. These graphs are provided by the manufacturer, and we might start with the bottom one. One of the characteristics of CMOS sensors is the relatively low read noise, particularly as you increase the gain as measured in decibel units. In this particular graph, each unit is 0.1 of a decibel. As the gain drops to 0 decibel units, then the read noise increases. But in my sort of environment, even though people emphasize the importance of low read noise, in most suburban environments, the greatest amount of noise is shot noise. So I don't think that that's a particular advantage in my case. There's a big difference in dynamic range between the high end of the gain and the low end of the gain. But I found that that's not a particular concern of mine because with 12 bits, I like to have comparison stars that are relatively close in magnitude. It's useful for the upper two graphs to have a look at them together, and I've modified them here slightly. Unity gain, 1 electron per ADU, occurs at 139 decibel units. That equates to 4K electrons in the full well, which is what you expect. If you change the gain to 5 electrons per ADU, that's what gives you the full well of 20K, which of course is simply 5 times 4. Linearity is quite good, but the results of the linearity testing do depend on the gain. This particular plot shows the linearity of 5 electrons per ADU. And the gain is pretty much linear until you get very close to saturation, which occurs around about 56,000 ADU. Interestingly, this is a 12-bit camera, so that you should only have 4,000. The manufacturer has decided to multiply that result by 16, in other words, shifting the bits, so that your readout at maximum ADU is in fact 65,000, I'll show you in the next slide, which is the linearity when you have 1 electron per ADU as the gain setting. Again, the linearity is quite good, and the linearity extends until quite close to the saturation, which occurs at 65,000 ADUs approximately. And you can see that, of course, if you do a line profile through a defocus star, which is in fact saturated and is precisely at 65,504 ADU. Because of the way I use this camera, which I'll explain shortly, I'd just like to spend a little bit of time on transformation coefficients. This is the ZWO camera with Johnson B and V photometric filters. Now, as is usual with CCD cameras or other monochrome CMOS cameras, the color index transform approaches unity, approaches 1. For this particular plot, the actual coefficient is the inverse of the slope, so it's just over 1. The transforms for the individual filters, the Johnson V here and the Johnson B here, alternatively, or in this case, approaches 0. In this case, the actual slopes of the curves or the plots represent the transform coefficients. That's quite different from what you get when you do transformation coefficients with a DSLR camera. In the case of the color terms here, B minus G and G minus R, the correlation is good, but the slope is nowhere near unity. In the case of the individual color channels, here the B, and then on the top right, the green, and again the green, this time plotted with B minus R, and finally the red channel. The correlations are good, but none of these actually show a transform anywhere near 0. And finally, a different filter set again. This arose because these are the RGB astrophotography filters that actually came with the camera, or I ordered with the camera. Someone mentioned on the AAVSO discussion forum some time ago that they tried transformation coefficients with astrophotography filters, and I did it just out of curiosity. Again, the color terms show good correlations, but in fact, they're nowhere near unity. And in the case of the blue and the green filters, the transform is nowhere near 0. But, and this is the point of looking at transformation coefficients, in the case of the red filter, the transform with both B minus R and B minus V is very close to 0. What this sort of thing means is that if you have a transformation coefficient of 0.01, if you do non-transform magnitudes, calculate non-transform magnitudes, then if you have a difference of 1 magnitude unit between your comparison and a variable star, the error due to the transform will only be 0.01 of a magnitude. So this means it's possible to do non-transformed magnitudes with this particular filter and still get reasonable accuracy. And that's what I decided to do. This just summarizes the situation, but I think I won't waste time by concentrating on this slide, except that I've highlighted the fact here that with the red filter, with the ZWO camera and an astrophotography filter, you get a transform coefficient that is close to 0. It's worth, when you're thinking about transformation coefficients, just thinking about the relationship between Johnson-Cousins transforms, or the bandpass for each of the 3 filters, and what you get with a DSLR camera. In the case of the green and the red filter, the peak transmission is close to the same for both sets of filters. Not so for blue. For the DSLR camera, the peak blue transmission is shifted redwards. In the case of the green DSLR filter, there's a lot of extension of the capture of the light to bluewood. In the case of the red filter, the Cousins filter extends much further into the red than does the DSLR filter. But the DSLR red filter extends more bluewood. So they don't correspond terribly well. But as long as the stars are approximately black body, then that's not too bad. In the case of the ZWO astrophotography filters, which are interference filters, the situation is totally different. Here you've got approximately rectangular profiles for the transmission curves of the filters, and each of them has a flat top. One of the characteristics of this particular situation, or this particular filter, is that the hydrogen alpha is captured beautifully by the red filter, whereas it's not, for example, with the DSLR red filter. So it's this filter on the right, the ZWO astrophotography red filter, that I decided to use for photometry. The validity for this is that the relevant transformation coefficient is near 0. Therefore, non-transformed red filter magnitudes are close to Cousins R. And I did that only because I'm using results only for eclipse minima timings and not for any other purpose. Advantages include the fact that red wavelengths are less affected by EMS, and that many stars are brighter in R than in V. But there is a requirement that the Cousins R of the comparison star must be known. Therefore, the V minus R of comparison stars must be found, so that RC can be calculated from V minus the color index. Now, to get the color index, I use the Tycho 2 spectral type catalogue in Visia, which is catalog 3231. If you enter the Henry Draper catalog number into the search box, you can scroll down and obtain the spectral type of the star. And in particular, you can see the luminosity class, which is here beside the red arrow, which is what you need for the spreadsheet that Mark Blackford kindly gave me. If you put the B minus V color index into this cell here, the spreadsheet will calculate the V minus R value depending on the luminosity class of the star that you are actually needing it for. These particular relationships were obtained from this publication back in 1993, which used high order polynomial functions to show the relationship between different filter systems. So with the camera and the filter wheel, I first used it attached to a 120mm f7.5 refractor. And with 9th magnitude stars, this gave pretty good results. There's quite good stability and the precision was quite good. This is the eclipsing binary star V610RE. This data was obtained from a heavily defocused image, as you can see here. And this is the line profile of the variable star, and it has a full width half maximum of 22 pixels, quite a heavily defocused image. But this year, and just before this year, I decided to move to a different setup. The same camera, the ZWO camera with the filter wheel, but coupled with a Canon 200mm lens, f2.8, and there's a ZWO adapter here, which enables the lens to be coupled through the filter to the camera. If you had a color camera, then the adapter would in fact be a longer cylinder, which in fact would account for the spacing occupied by the filter wheel. The advantage of this setup is that it's an equatorial mount, and does it show here? No, we'll talk about the functionality of the mount later. I went to this system because I'm not getting any younger, and I didn't want to maintain a very heavy telescope and mount setup so that I could in fact use a portable setup quite quickly. This is not a go-to mount, and it does require that by a system of iteration and astrometry, you approach the target slowly over a period of time. I don't auto-guide, although it's possible for this system to be auto-guided. But I find that with good polar aligning, that's quite sufficient for working several hours each night. It's an equatorial mount, and of course, one of the disadvantages of equatorial mounts is with a meridian flip, you can get a disconnect between the two parts of the light curves. But an advantage of this system is with the offset to the front of the mount, it's possible to, in most cases, arrange the setup of the camera and the mount so that it can be tracked for quite a few hours without actually colliding with the mount, the camera colliding with the mount. Sometimes you use the standard setup like this, but at other times it's possible to invert the camera and the lens, which, as long as the star is high enough in the sky, gives an enormous range of hours across which the star can be followed through the night. And when you do that, it's possible to get long light curves over 7 or 8 hours without there being a meridian flip. This is quite a bright star, and you can see that the photometry, I think, is quite good. That image was defocused, or the image on which that photometry was done was heavily defocused, as you can see here. But I did decide to experiment with star images that were sharply in focus, which is what the AAVSO people recommend. And sometimes that doesn't work very well. This is QW telescopii, and I don't think I'd try this particular star again because it's got a very low amplitude, but I just wanted to concentrate on the check star light curve here, which to me doesn't show very good precision. They were exposures of 20 seconds with a cadence of about 43 seconds through the Canon f2.8 f2.8 lens. The gain was nearly 5 electrons per ADU. So I wasn't particularly happy with that. But in fact, this is another star with the same sort of magnitude, with the same setup and exposure and a much better outcome in terms of precision. So I suspect that what was happening here, there may have been some atmospheric effects that I wasn't aware of. So it is possible to get good light curves with sharply focused stars, but they do vary. This is the sort of image that you get in sharp focus, of course. Here's another eclipsing binary, CN Indy. In this case, the check star magnitude was actually about 9.5. So the precision there was quite reasonable as well. Again, a sharply focused image. So I found that the setup does work in fact quite well. And during 2022, even though the weather has not been entirely good for most of the year, I was able to take and submit minima on 12 stars, 19 minima from 12 stars to the VSS database, which I think was quite a reasonable effort for this year. But I just go back to the issue of in-focus or defocused images. I've got some quotes here from the new CCD CMOS photometry manual of the AAVSO. And as usual, the recommendation is that for best photometry results, the focusing should be such that the full width half maximum of the seeing disk is spread across 2 to 3 pixels. And that should optimize the signal to noise ratio and improve precision. So if the full width half maximum is less than 2 pixels, that is undersampling. If it's more than that, it's oversampling, as we all know. But the comment is made that either situation could affect the accuracy of photometry. And a similar comment to that was made in the previous CCD guide to photometry. But in the new manual, the comment is made that oversampling is not nearly as serious as undersampling. That still implies that oversampling is a problem. Certainly with undersampling, you can lose information. And down the bottom, it says, fine photometry is possible when somewhat oversampled. I just don't know what somewhat means. This is the image I showed you previously that I took through the camera, the new camera. And I think this is severely oversampled, not somewhat oversampled. And yet I think this is fine photometry. So as far as I'm concerned, I think that the word somewhat should be removed, although I'm not one of the editors or contributors to the manual. So I think that it is, with this camera, it is my feeling that probably the best photometry is obtained when there is defocusing of the image. It may depend on the brightness of the star. I'd just like to finish with some work done by others, Ed Wiley and Ken Menzies, who are senior observers with the AAVSO, and they published this work this year on the accuracy and precision in amateur photometry. And they studied both CCD and CMOS cameras. And they found that there were no statistical differences between 16-bit CCD and 12-bit CMOS cameras. Both were capable of median accuracy of 0.02 magnitudes or less. Now, the 12-bit CMOS camera was in fact in the New Hampshire, one of the New Hampshire observatories, the Bright Star Monitor in that area of the northeastern United States. Of course, that camera was attached to a Takahashi Epsilon 180mm f2.8 astrograph, which is a very high quality instrument, which of course has a much wider aperture than my Canon camera lens. The camera was the ZWO ASI1600MM camera with many pixels at quite a small pixel size. So it was with that camera and that setup that these authors regarded the fact that they could get very good photometry, even though it was a 12-bit camera. And I think I'll leave the final words to Ed Wiley, who in a Cloudy Nights post about a year ago said that, of course, 16-bit is desirable, but you can do good photometry with a 12-bit camera. And Ed has been an instructor for the AAVSO online courses in CCD photometry since 2016. So I don't think he's going to make a comment like that without some justification. So I'll leave it at that. Thank you very much.
Well, thank you very much, Roy. I must agree wholeheartedly with you regarding the oversampling. There's no problem at all. I think where it might be an issue is if you have crowding of stars. So the overlapping star images will impact on the actual accuracy of the measurement. So if the star is truly 10th magnitude, but there are overlapping star images from nearby stars, then the measured magnitude might be 9.9. So the accuracy might be wrong, but the precision shouldn't be affected. You'll still get the same nice curve. Where it becomes a problem, oversampling might be a problem, is when the actual intensity in each pixel is very low. So you might get some issues with noise being a limiting factor. But if you choose your exposure times so that your star images have high pixel counts, ADUs in each pixel, but not saturating, I think an oversampled star image is perfectly fine.
Yes, I'd agree entirely. And the very best photometry I've been able to obtain, either with the DSLR or with the CMOS monochrome camera, is precisely that, where the image is defocused and where the well capacity is as close as possible to the upper limit of linearity without in fact saturating the star image. Yeah, over 50% of the well capacity should be perfectly fine. Yes. Could I make one more comment? I use AstroImage J for my photometry, aperture photometry. And one of the settings there, which is selectable by the user, is to remove background stars. And that simply means that if in the annulus there is any star or parts of a star, the setting will in fact remove any pixels that are more than 2 sigma above the average in the annulus. So you can in fact still have some signal in the annulus, even if it's significant, and get rid of it and prevent this problem that Mark described so very well. Of course, you've still got to make sure that you don't have blended stars within the aperture, which is another issue with defocus.
Yeah,
and it's probably best out of the Milky Way. For example, tonight I've got a target I'm hoping to look at in Grus, which is fine. The stars are well separated there, and it's ideal to do this sort of thing if you're outside of the plane of the Milky Way.
Yeah, okay. Any other questions? Yes, Greg.
This is going to reveal my ignorance, but well, if you don't ask questions, you never know. I had a camera which I've sent back to China for repair, and it seems to have been caught up in the COVID-19 lockdown. It's nearly 2 months, I think, since I sent it. So I'm looking at buying another ZWO camera locally from either Testar or Bintel. And it seems from what Roy has said that the 12-bit issue is not really a problem. That he's been able to do quite accurate photometry. And I notice there's also 14-bit ZWO cameras. I'm wondering also about the issue of dynamic stops, and I really don't understand dynamic stops. I understand analog to digital units and that you've got much finer representation of those changes across 65,535 different levels of brightness. But can you explain to me dynamic stops and how that might affect the ZWO cameras?
I'm not sure that I can be regarded as any sort of expert on that, Greg. My understanding is that it relates to the range in camera stops across which signal will in fact be recorded on the sensor. And I think I can understand that, but as I said, that's not something that I regard as very important with a 12-bit camera, where it's really necessary to maximize the signal to try to get to near as full well you can within the linear range. So I don't want a large range of brightness in my comparison stars. I want quite a small range of brightness so that I can push the brightness up or the signal up as high as possible. I don't know what other people think about that, but that's my attitude. The other thing is, if I decided to spend a lot of money, I would definitely go for a 16-bit camera. But it's just that was my decision at the time.
I've got a question, Roy. With eclipsing binaries that have very deep eclipses, is there an issue with the 12-bit ADU range, or do you think that's not such an issue?
I don't think I've actually had any such stars as my targets, Mark, so I can't really express an opinion on that. I'm sure that if that were the case, I mean, for example, some of the EA binaries, and I don't normally target those, I'm sure that the precision would drop off as you got down towards the minimum of the star, because the precision would be less there than it would be toward the top of the curve, which is where you would be closer to saturating the pixels.
Yeah, okay. That's how I understand it as well. If we have no further questions for Roy,